So now let's see the proof. Proof. What we have stated is that delta variation of the expectation value of energy will give you raise to the equation of motion. So rewrite the earlier equation in this format. We take the denominator from the right side to the left side, then this becomes scalar product psi or norm square psi into E, where E is the energy eigenvalue of the relevant quantum state, whether it is ground state or excited states, whatever may it be, say E. And here you will have to keep in mind that energy is a scalar quantity, but all others are vectors. Equal to, on the right side we have this quantity remaining, scalar product psi h psi. Take the delta variation of this equation. Delta variation will be following a product rule on the left side, as there are two different terms. So first function into derivative of second, delta variation of E, plus second function, that is E, into derivative of first. Here you have two vectors, one in the ket space and the other one in the adjoint ket space. So delta variation of the vectors in both spaces are to be taken into consideration. Then the overall variation will be the sum of these two terms, scalar product delta psi plus scalar product psi delta psi into the second function, that is E, equal to, on the right side we will have to account for the delta variation of, say, psi in ket space as well as in adjoint ket space as well as in adjoint ket space, and H will not have any delta variation as it is an independent operator. Then this becomes delta psi h ket psi plus scalar product psi h ket delta psi. That is, you take the second term on the left side to the right side, then this becomes scalar product psi delta E equal to, on the right side you already have this term, these two terms that we have written here, and this term coming from the left side will be written as a two negative terms, minus scalar product delta psi E psi. Yeah, I have also given E to the operator domain in the scalar product psi E delta psi. Now we can combine this term with this one, and these two terms can be combined to make this equation as scalar product psi into delta E equal to scalar product delta psi. You have these two terms exactly identical with the delta variation for the wave function in the adjoint ket space. Here in the operator domain you have a specific operator H, that is Hamiltonian, and here you have an eigenvalue or a scalar parameter, say E. So this could be combined as a scalar product delta psi H minus E ket psi plus scalar product psi. These two terms upon combination give us scalar product psi H minus E ket delta psi. That is, scalar product psi delta E equal to delta variation of this quantity overall. It is exactly in this way we have taken the delta variation of this term, and here we will be performing the reverse. Delta variation of scalar product psi H minus E ket psi will be there on the right side. Apology for this curly bracket, actually I meant a normal bracket, but delta E will be equal to 0 because E is the energy corresponding to a stationary quantum state. That will be always a constant, and its delta variation will be then, total variation will be then 0. Then we obtain this as a delta variation of scalar product H minus E psi equal to 0. For an arbitrary choice of psi, yeah, I have forgotten to tell you about this choice. Actually not forgotten, it is put aside for the upcoming session, what exactly the nature of this wave function psi, because I have already told you that we will be applying variational method in those problems where we are totally ignorant, not totally ignorant, ignorant about the format of the wave function representing the system, but we must have some knowledge about the properties of these wave functions corresponding to the problem. So delta variation of psi h minus e ket psi equal to 0 is to be satisfied for an arbitrary choice of psi. That is possible if and only if h minus e operating over ket psi equal to 0. It has two different manifestations. H minus e operating over the vector in the ket space equal to 0. H minus e operating over the vector in the adjoint ket space also equal to 0. Delta variation of this overall quantity means delta variation of this one plus say this quantity. That is to be equal to 0 means these are separately equal to 0. That means h minus e operating over a state function with this particular wave function will be always equal to 0. That means h operating over psi, ket psi equal to e times ket psi, which is nothing other than the fundamental equation of motion in quantum mechanics referred to as the time independent Schrodinger's equation. As we are going to make use of this method as an approximation method for time independent problems, we have generated the equation of motion in time independent problem, that is the time independent Schrodinger's equation. And this proves the applicability of variational method in quantum mechanics as well. Rather than proving this applicability, we will be interested in exploiting this method to make some knowledge about some problems that cannot be solved following perturbation procedure, or in the case of those problems where we have an idea about the Hamiltonian but we are ignorant about the actual format, totally ignorant about the actual format of the mathematical format of the wave function representing the system or the problem. So now we will specifically talk about the principle of variational method being applied to quantum mechanics. So in quantum mechanics, I have told you the essential idea is the evaluation of the expectation value of the Hamiltonian of the system, because we only know the Hamiltonian of the system under study. And from the fundamental postulates of quantum mechanics, we know that expectation value of H means scalar product psi H psi, provided psi is a normalized wave function. If it is not normalized, of course, you will have to normalize it right now. For that, you will have to divide this equation by square of the norm of the vector, scalar product psi by psi. I have written this equation under the assumption that psi is a normalized wave function. If psi is not normalized, we will have to incorporate it here. Then what about psi? I have told you that this is applicable in the case of problems where you have no knowledge about the wave functions. It is a trial wave function. It is a wave function that we assume following some educated guess or following some genuine guess about the physical intuitions of the problems. So that is the nature of psi. If so, then you can prove that even the ground state energy of the problem under your consideration will be less than or equal to the expectation value of H. This is what I have told you, that this variational method always give you an upper bound value for the eigen values. That is, even that is the exact ground state energy, for I am going to evaluate this as ground state energy. If I meant that this is the energy of a particular quantum state, I can take it in that manner. But I have already made it clear that generally variational method will give you a suitable calculation only for ground states. So I will not be confusing you. This I do for ground state energy. That will be less than or equal to expectation value of H. It means that it will never go above expectation value of H. Most often, if you are lucky, you will give you a value that is equal to the ground state energy, or that will be exceeding, say, the ground state energy. The expectation value that you evaluate will be exceeding the ground state energy or will be equal to the ground state energy. Then you have a choice that if you have made the wave function properly or following a proper guess, then definitely this will give you a value equal to the ground state energy. This mathematically we can prove also. So expectation H give you an upper limit of ground state energy. I have taken it for ground state. Let's set ket phi k. Yeah, I have forgotten a ket symbol here. Anyway, I meant it as an orthonormal basis. Form a complete basis. Then any wave function, whether it is trial or an exact wave function, may be written as a linear combination of these basis vectors. Summation over I, A, I, phi, I. A ket is understood here also. Then expectation H, where let me assume that psi is a normalized wave function. It is written in that manner because phi I is assumed to form, or set ket phi k is assumed to form an orthonormal basis. Then expectation H equal to scalar product summation over I, A, I, phi, I, H operating over scalar ket summation over J, A, J, phi, J. So we take the expansion coefficients out of the scalar product from both adjoint ket space and ket space. Then this becomes summation over I, A, I star coming out of the adjoint ket space or the prefactor space. Summation over J, Aj as such coming out of the ket space. Then this is summation over I, summation over J, Ai star Aj, scalar product phi I, H, phi J, where phi J is assumed to be an eigenket of H. Then H operating over phi J is nothing other than Ej phi J. Ej is a scalar, so in the vector part what remains is scalar product phi I, phi J, which is say phi k's are forming an orthonormal basis. So scalar product phi I, phi j is nothing other than Kronecker ij. So this is summation over I, summation over j, ai star, aj, ej, Kronecker ij. Yeah, evidently this Kronecker will have a value if and only if I equal to j. So we put that limitation I equals j, then replace j by means of I, summation over I, ai star, ai, that is ai square explicitly. Ej becomes ei equal to summation over I, ai square. Let me split ei, the energy eigenvalue that we evaluate following this approximation procedure, as E1 plus delta E, where delta E can be positive only as it is corresponding to a bound state. So E1 plus delta EI, where E1 is the exact ground state energy. Then this is summation over I AI square E1 plus summation over I AI square delta EI. Summation over I AI square following normalization give you a value equal to 1. Then this is E1 plus summation over I AI square delta EI. I cannot put here it as a 1 because I have to account for a product term here. But this term involves AI square and delta EI. AI square is positive definite. Delta EI I have already told you this also positive. Then this energy will be exceeding that of the ground state energy by an amount, say this one. This is what I have told you, that E1 will be less than equal to expectation H. Expectation H what I have evaluated is found to be, say, this one, which is exceeding the ground state energy by this amount. That means the variational method always give you an upper limit for the ground state energy. I have already told you why it is ground state energy. You can apply the method for excited state as well, but in ground state itself there is a limitation that we have already seen, and definitely there will be those limitations in excited states, and further the accuracy will be much limited in excited state. Now we will see, so now you might have a vague idea about the applicability of variational method. Now we will see a more vivid idea about the procedure of applying the variational method.